Hi everyone. In this video, we will talk about the direct torque control and how the classical DTC, the DTC abbreviated is for the direct torque control. So the how classical DTC creates a torque ripple problem and how it is different from the field oriented control. So as we have earlier seen in the previous videos that how the FOC works, and both the FOC and the DTC both works to control my AC motors. So it is applicable for my induction motor, it is applicable for my PMSM motor, it is applicable for my SRM motor. All these three kinds of motors are being used in the electric vehicle. And currently the PMSM motor is widely deployed in all the EV models in the Indian scenario as well as in the globally. So let's understand that how the DTC works and how it is superior from the FOC control. So the DTC, the direct torque control strategy used the torque and the flux decoupling, and it directly controls my torque and flux from my stator voltage and the current. So here it is shown that the flux and torque estimation is being done after taking my stator and the voltage current uh, of the motor, and then the flux and torque estimation is being done based on the modeling which we will see in the separate video, that how flux and the torque is being decoupled through my voltages of stator, and based on that it creates the uh, error between the flux, reference flux, and the reference torques which we need to control, and takes the error which goes into the two different kind of a controllers. In FOC we have seen that we have used the PI controller, but in the DTC it uses the hysteresis controller. So for both the hysteresis controller, for the flux and the torque, the error goes in both the controllers, and accordingly based on the hysteresis band, whether if the error is within the predefined limit, the switching of my inverter does not happen. If the error crosses the predefined limit of my hysteresis controller, then it gives the command to my inverter switching based on the lookup table. So this is the lookup table which again is based on my voltage. Uh, this is again based on my voltage vectors, which we will see just in a few seconds, that based on the voltage vector lookup table has been created, and it defines that whether we wants to increase the flux or decrease the flux, and similarly if we want to increase the torque or the decrease the torque. So based on that the lookup table has been created, and it gives accordingly the switching signal to my inverter. So that inverter again controls the torque and the flux of my motor which is being in control. So this is the overall DTC concept, which uses the flux and the torque estimation based on my stator voltages. So the DTC uses the basic modeling concept of the AC motor, whether we are talking about the induction motor or the PMSM motor or my synchronous reluctance motor. So all these three motor has one thing in common, that the stator of all these three motors are works identical, and all three motors has the revolving magnetic field or RMS being created from the stator supply. So taking that modeling into account, the torque of all these three motors, whether it is a AC, PMSM or SRM, is having the relation with respect the torque relation with respect to my lambda s. Lambda s is nothing but the stator flux, and is is nothing but the stator current. Similarly, the other voltage equation for these kind of a motor is that Vs is equals to this is ISRS, which is the drop is happening inside my motor over the stator winding, as well as the d uh, lambda s by dts dt. So this is nothing but the d phi by dt, which is creating a induced EMF over here. So this is my voltage equation. Here we can see that again the flux, which is lambda s, again depends on my stator voltage, and similarly the torque, which is given over here, again depends on my stator flux. So by controlling the voltage, stator voltage, I can control the flux as well as the torque, which is known as the decoupling. And the detailed modeling of these AC motors and how the DTC works, we will see in the separate video. So here we have the classical DTC structure, and the classical DTC uses a simple yet effective control structure with the real-time estimator and hysteresis band for regulation. So here we can see that just now we have talked about, here we have taken one example that if let's say I want to control my induction motor, so taking the feedback of the induction, the stator current and the voltages over here. So this went into the stator current and voltage computation, which is nothing but the continuously monitoring the stator current and the stator voltage. So this is nothing but the continuous monitoring of my stator current and the stator voltage. Based on that, it creates, or based on the modeling which I have just to give you the glimpse, and we will take the another video in which we are going to in-depth modeling. So based on the modeling, it decouples my stator flux computation, the torque computation, both. So based on the voltage measured and the current measured, it measures the what is the flux situation and what is the torque situation, and it goes into both the values, the stator measured stator computation and the torque computation goes into the two separate controller. So this is the hysteresis controller for flux, and this is the hysteresis controller for my torque, which is separately shown over here. So this is shown over here. If let's say this is one, so this is the hysteresis control for my torque, and let's say if this is the second controller, so this is my flux controller or flux hysteresis controller. And we have also given the reference value of the torque and the reference value of the flux, which we want to have it to control my motor torque and the flux over here. So what happened exactly, I was just want to control my motor torque and the speed. So therefore I'm just decoupling the torque and the flux from the taken stator voltage and the stator current, and this measured value is being compared here. This is the comparator. It is compared here for the both the torque and the flux value, and the error goes into these two. So the torque error which is being produced, let's say delta TE, and similarly this is let's say delta uh, xi s, the stator flux shown over here in this figure. So based on that, the controller sees that if this error is within the predefined band, so this is nothing but the band over here. So this is the band for the flux, and this is the band for my torque. So it sees that if the error is within the predefined band, then the controller does not give any command for the switching. So the switching table also does not come into the picture if the error is within the predefined limit. However, if the error goes beyond the predefined limit or beyond my bandwidth of the hysteresis controller, here I just want to give you one uh, logical concept that the band of these controllers are within our hand. We can change the band of this according to the control of my motor. If I want to have the more smooth control, then I can reduce the band of this hysteresis controller. So if the error goes beyond the band of the hysteresis controller for both the flux and the torque, then accordingly the switching table, the output of the controller goes into the switching table, and it selects the vector, switching vector, which has to uh, go into the my inverter switching, and accordingly the inverter switching happens, and then it controls my stator torque and flux over my induction motor over here. Okay, all right. So here again, the error goes into the hysteresis controller, which decides accordingly that if, let's say, that this error is within the limit, and but the torque error has outside my band limit of this hysteresis, so accordingly it will select a vector where I do not want to alter the flux, but I want to increase or decrease my torque. So accordingly, the voltage vector will be selected from this switching table, and then it will goes to my inverter, and inverter switching will happen accordingly, and then it will control my induction motor output. So here it is just a glimpse of the voltage vector selection, how the voltage vector is being defined for the in the classical DC DTC. This is the example for two-level inverter switching. So two-level inverter switching, how it is happens, and how the voltage vector is being selected. For that, again, a separate video where we will have the in-depth mathematical modeling. There we will take all these vectors, that how these vectors being defined. Here, uh, just to give you an idea, this SA, SB, and SC, these are the three switches of my two-level inverter. So if I have an inverter, so accordingly, for that, let's say these are the switches. So in one lag, I will have the two switches of uh, inverter like this, and from here this will be connected through the DC input, and then a three-phase load will be connected to my this inverter lags. So three-phase load will be connected. So SA is the upper switch, SB is the upper switch of the second leg, and SC is the upper switch of my third leg. So if the status of SA is 1, so the lower switch of the same leg will be SA dash. That means if this is 1, then very obviously it will be 0, because I just want to avoid the short circuit in this case. So similarly, this is SB dash, and similarly this is SC dash. So based on that, the switching SA, SB, and SC is being shown over here, and the switching vector is being divided into the 6 vectors and the 2 0 vectors. So VA to V6 are the switching vector for this kind of inverter, two-level inverter, whereas the V7 and V8 are my 0 vector. V0 and the V7 are my 0 vector. So the first vector, which is shown over here, 1 0 0, it shows that this is 1, this is 0, and this is 0. So that means SA will be 1, so this switch will be closed. If SB is 0, so that means SB dash will be closed, and SC is 0, then SC dash will be closed. So these three switches will be in the action. Similarly, for the V2 also, it shows that 110, the vector V2 is 110. So it shows that one SA will be closed, SB will be closed, and SC dash will be closed. So accordingly, the 6 vectors are there, and V0 is 000, and similarly the V7 is also 000. So all V7 and V0 uh, 111 and 000, so it does not produce any output because all the switches will be open, all the three switches will be open, and there will be no output. So this is the vector which is being used in the classical DC. And how does it come, and how it controls my voltage and the flux and the torque from the voltages. So when we'll have that the in-depth modeling video, there we will understand that how it is happening. However, the DTC suffers from the torque ripple, and this torque ripple, why does it happen in the classical DC? Because the DTC uses the discrete voltage vector switching, which causes the abrupt change in the torque. So suddenly, if it's something like that, the step change in the torque is happening. So let's say this is the some value. So suddenly from one value to another value, something like that. So let's say this is the previous values was happening, and suddenly I have changed the torque in the step values of my motor. So we will see some kind of a jerk and the torque is being created in the motor. So that happens. And the DTC controls, in the DTC control, it uses a lookup table which we have just seen to select the discrete voltage vectors like V1, V2, V3 up to V6 based on the torque and the flux error which is being created from by the uh, comparator, and then that error goes into my hysteresis controller, and accordingly the discrete vector has been chosen by the lookup table. So this vector are applied directly without modulation, which leads to the step change, where just now we have seen that this is the step change, something like it happens, which creates the sudden change in the torque and creates the torque ripple. Moreover, the hysteresis band used for the torque and flux control allows error to oscillate within a set range, because we have seen that there is a band and the error oscillates within that band. So as the torque and the flux oscillate within the hysteresis band, the inverter switching is not smooth, again, which is causes the torque ripple. And also the switching frequency in classical DC is not constant, because it depends on the torque and the flux error, and it is continuously changing based on my actual motor performance. So this irregular switching also introduces the harmonics and contributes the torque ripple. So these are the major reasons of my torque ripple, which is again here briefly shown that the three major regions are: one is the variable switching frequency, which is happening due to the error created by my controllers, which is dynamic. Selection of the voltage vector again is happening in the discrete level, so that the discrete switching is also happening, which creates my again the torque ripple. And the interaction between the flux and the torque error are coupled, and the abrupt voltage switching causes oscillation in the both the values, whether it is the torque and the flux. So these are the major causes of my torque ripple. And the torque ripple, as you know, that it can create the mechanical vibration. It will also degrade my efficiency of my motor, which is being used for my different applications, like if I'm using for the EV, and if the torque ripple is happening, I will feel the jerks while running my EV. So this is not the desirable scenario, which this has to be eliminated. And increased wear and tear will also happen, because sudden change in the stuff form will happen, and which again will cause my sudden torque ripple, which again creates more wear and tear of my motor. So what are the techniques by which we can control these torques? So the main which is being used nowadays, that is the SVM, or the space vector modulation. So this space vector modulation up to some extent reduce the torque ripple which is being created by the classical DTC. Also the improved control algorithms, if I just want to use the more optimized hysteresis band, which can further reduce or help to reduce the switching frequency. And if the switching frequency is also getting smooth, or it is somewhere like almost it looks like a constant, or the very small step changes is happening, again which leads to the less torque ripple. And also reducing the size of the hysteresis band again can minimize the fluctuation in the torque and the flux. So talking about all these DTC introductory level brief, so now we can compare that how FOC and DTC, they both are different. So this is the main thing, that in FOC we uses the transformation. So initially from ABC 3-phase to alpha beta stationary frame to the rotating DQ uh, transformation happens in the FOC, and again the inverse transformation is also being used in the FOC. Whereas in the DTC, directly torque control and the flux without explicit decoupling is happening. Although it is uses the alpha beta reference frame in the DTC, but the transformation does not require so much complex controllers and so much complex computational efforts in case of the DTC. So we can say that DTC is less complex in terms of the implementation as compared to my FOC. The torque equation for both FOC and the DTC, I can say that in case of the FOC, it is takes the rotor flux, whereas in the DTC, it directly controlled from my stator flux. The controller, we have seen that in the FOC after the transformation, converting in the DQ axis, which is nothing but as it has seen as the DC quantities. So PI controller is being implemented to control my motor torque and the flux. Whereas in DTC, the hysteresis controller is being used, which uh, checks the error. If it is within the band, then no switching will be happen. If it beyond the defined band, then the switching action will be taking place according to my lookup table. As we have just stated that FOC is more complex in terms of the implementation because of the transformation is being done over there. Advantages, FOC gives the more precise control because we have seen that in the DTC we have the torque ripple phenomena there. So therefore, more precise control happens in the case of the FOC, and there is very less torque ripple as compared to DTC. Whereas in the DTC has the faster dynamic response because there is no Clark's transformation is being happening, no Park's transformation is being happening over there. Um, explicitly, so therefore it gives you the faster response to any change in the motor torque and the load requirement, and it is very simpler to implement without requiring the DQ decoupling. So I hope now we have understand and we have the idea about the DTC at the introductory level. In another video we will see in depth modeling of my AC stator reference frame, how the voltage is uh, being controlled to control my flux and the torque independently, and how the voltage vector is being selected or the lookup table is being created to control my voltage and to control my torque and the flux. Thank you.